My name is Gordon Hilton Fick, and this video is an introduction to the Junior Exocet. It's my intention to go through the establishment of the pattern that is considered the Junior Exocet. There are many variations of this, but I'm going to be illustrating what is probably the most common one. And a little bit of background before we get started. The pattern that we now, or the technique that we now refer to as Exocet, appears to have been first used without name by Alan Barker. Somewhat later on, it became known as the bye-bye technique. Then Champagne established the general conditions for an exocet. Champagne appears to have first used this naming of exocet in 2009. Now, the exocet is a large collection of techniques. The Junior Exocet belongs to the set of techniques known as Exocet. And the Junior Exocet is called a pattern because it can be when one discovers the pattern, immediately go to a collection of exclusions, as I will illustrate. The use of what we now call the Junior Exocet was established in 2012 by David P. Bird. Indeed, in April of 2012, David refers to this pattern as the Junior Exocet. So there are Junior Exocets, there are Senior Exocets, then there are General Exocets. One sees sometimes abbreviations for these terms, and there's a whole waft of material here concerning the Junior Exocet. Indeed, what is highly recommended to everyone watching this video is to study the very detailed and authoritative documents established by David P. Bird called his Compendium. It turns out that even since the time of the Compendium, there have been some improvements and changes and enhancements. But what I intend to show you in this video are what were essentially the core parts to the Junior Exocet. And it will be a special version, I guess, but perhaps, as I said, the most common version. And that is with 2 base cells and 2 targets. And the targets are said to be unaligned. And I will illustrate what that means in a minute. I've chosen for illustration here a puzzle that will give us the opportunity to see essentially all of the, as I say, the fundamental parts to solving a puzzle that has the Junior Exocet pattern. We're going to begin then by using, and oh, did I mention that this is actually, the puzzle is actually from Andrew Stewart's website and is Unsolvable 225, for those of you who want to go back and look. All right, I think we're ready to start the solving. And I'm going to move with a lot of coloring and a lot of labeling. Not necessarily what you would necessarily need to do when you're actually using the methods, but I think it does help to see the colors of candidates put in and also the colors of cells put in. All right. Now we come to the first illustration. That is the position and placement of what we will see in a minute are the base cells. The digits in the base cells are 3, 4, 5, and 9, sometimes called the base cell candidates or base cell digits. We will notice that since the two candidates are in a row, that we will see in a moment that the junior exocet band or junior exocet chute belongs to the upper chute or upper band. Now we have the two target cells, and they are here and here. Now we'll notice, just to get us started, that the target cells contain some of the base cell candidates, 3, 4, 5, and 9. There they are, 3, 4, 5, and 9. And there are some additional cell candidates. These are, as we'll see, are referred to as the target cells. What we're going to be able to do at the very start of this is eliminate the candidates in the target cells that are not base cells. All right. Next is the display of what's called the mirror cells. Now, the mirror cells are here and here and here and here. So we'll call this target cell 1, and this is target cell 2. It turns out that these two cells are the mirror cells with target 2, and these are the two mirror cells with target 1, and I'll explain this in a minute. We then have the companion cells. The companion cells are, in fact, in this particular illustration, reside here and here. Now, the first rule that we must check is that the companion cells do not contain any of the base cell candidates. Now, this is obviously covered here because both companion cells contain gibbons. So that condition is satisfied, okay? But that's the first issue that needs to be checked. Now we'll establish what are called the cross lines. The cross lines are going to be, in this case, the column determined by the first target cell and the column determined by the second target cell. The third cross line is determined by the column that is in the middle chute or middle band, but is not seen by the base cells. Okay, it's almost easier to display them than it is to describe them. In this case, the cross lines are here, here. I'll put them all on here. Okay, those are we now have the two base cells, we have the two target cells, we have the two mirror cells, sometimes called mirror nodes or pairs of mirror cells, and we have the companion cells. Okay, now we come to the part of this pattern that is crucial to being junior, for the exocet to being junior. And that is that the base cell digits can appear in the cross lines no more than, in this case, 2 rows. So we'll illustrate those then. Let's start. Again, it's easier to display perhaps than it is to describe. So the first base cell digit is 3. And we can see that 3 in the cross lines appears here, and here, and here. Whoops. That's not what I wanted to do. I wanted to put digits in. Excuse me a moment. We'll go back to here. He's back. Now I want not the cell, but the candidates now. I'm going to be showing you the candidates. So we have a 3 here and here, and a 3 here and here. Notice that the base cell digit, or base cell candidate, 3, occurs in the cross lines in only 2 rows. It turns out that this cannot be more than 2, but for most of the illustrations that are, most of the patterns that I've seen, it is typically exactly 2, but it cannot be more than 2. And we'll refer to that in a minute. Now let's do the base cell candidate 4. We can see that it appears here, here, and here, 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 and here. Now we can notice, again, that the digit 4 is only in the cross lines in 2 rows. 5, we can see, is here, 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 and here. Okay, the digit 5 is only in 2 rows. Now let's do 9. 9 occurs here, 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 here. Okay, now we have things pretty much completely marked up for determining exclusions. It turns out that if the junior exoset condition is satisfied, that is, that the base cell candidates appear in no more than 2 rows in the cover lines. So in this case, the rows that are displayed here are called the cover houses. So we can see that we have rows 4 and 5 for the digit 4, 5 and 9 for digit 3, and so on. All right. Now, there is a proof in David P. Bird's compendium that basically says that if the junior exoset condition is satisfied, then the target cells must contain base cell candidates. That means we can exclude from this target cell, we can exclude 1. And from this target cell, we can exclude 8. Those are the first 2 eliminations that come from the junior exoset condition. Now, let's have a look at what I refer to, or what are described as, the mirror cells. The mirror cells for target 2 are here. They are row 2, column 2, and row 2, column 3. And for the target cell 1, the mirror cells are row 3, column 7, and row 3, column 8. Now we come to the second property, again proven in the compendium. And that is that each of the mirror cells must contain 1 base cell candidate and 1 non-base cell candidate. Must. Okay. That means that in these 2 digits, one of the 2 must be a base cell candidate and 1 must be a non-base cell candidate. Well, let's look at that. One of these 2 mirror cells contains a given that is a non-base cell. digit. That means that this mirror cell must contain a base cell digit. That means 1 is excluded. Now let's look over here at the second mirror cells. In fact, they are the mirror cells for the first target cell. We'll come back to that in a minute. So the same property of the mirror cells applies. One of the two digits must be a non-base cell candidate, and one must be a base cell candidate. Now we come to the next feature that often appears in the junior exoset pattern, and that is that the digit 6 here, while not a given, is locked. And we'll get this fixed. Oops. I keep on mucking this up. Hope you'll understand. Now we'll go to the candidates. Now we can notice that in the two target cells for the first mirror, the two mirror cells for the first target, that 6 is locked. So we'll highlight that. In other words, 6 must be in either the first mirror cell here or this mirror cell. In other words, the non-base cell candidate in the first mirror node, these two cells here, must be 6. That means that the other digit must be a base cell digit. In other words, it cannot be 8. And we can exclude the 8s. So here we can see that the non-base cell digit was a given. And in this pair of mirror cells, the non-base cell digit was locked. Okay. I find it helpful to keep on top of other exclusions that are implied from the current ones. Let's look. We can see that now, for example, that row 1 must be, that digit 1 in row 1 must be in the first block, because we've excluded the two ones here, right? So this is equivalent to now lock candidates. In other words, we now know that 1 cannot be here. That's a fairly standard lock candidates observation, right? We get a similar feature with the digit 8. Because we've excluded the 8s here, the only remaining 8s are in the first block. That means the only remaining 8s in the third row are in the first block. That means that these two 8s must be out. Okay. So now we've got a fair number of exclusions. And if we were doing this with a real puzzle, we wouldn't be just highlighting them in red, we would be deleting them. We would be removing them from the puzzle, either crossing them off if we're doing a paper pens method, or using the software to remove the candidates. Now we come to the next feature of the junior exoset pattern. And it comes down to a a more subtler understanding of what we know about the mirror cells and what we know about the target cells. Now, what can we see? Let's look at these two mirror cells. It turns out that the base cell digits in mirror cell 2 must be the same as the base cell digits in target cell 2. In other words, we can see here that since the mirror cells connected with target 2 are only 4 and 5, we then know that this target cell must contain 4 or 5. In other words, we can exclude the 3 and the 9. Okay. Whew. Well, we've got now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 exclusions so far. And I've illustrated now the exclusions to the target cells, the exclusions to the mirror cells, and the additional requirement of the fact that the mirror cells must contain the same base cell candidates as the target cell that they are linked with. And that gave us these last two exclusions, 3 and 9. Okay, now we're ready to describe the next technique that goes very closely with the junior exoset. And that is the notion of incompatible base pairs. Now there's one that we get very quickly here that I'll show you first. And then I'll show you the more elaborate incompatible base pairs method second. Now, we can focus our attention now on the fact that target cell 2 contains only 4 and 5. That means that the base cells, we don't know which yet, but the base cells must contain either a 4 or a 5. Okay, so either this 4 will be true, or this 5, or that 5. We don't know yet which one. But there's something hidden here. And that is that 3 cannot go with 9. Let's look. If 3 goes with 9, that means the 3 is here and the 9 is here. And there's no place for the 4 or the 5. But notice the target cell, the second target cell, contains 4 and 5. So we now know that the base pair combination 3 and 9 is incompatible. We cannot have 3 with 9. Now that in and of itself does not lead to any exclusions, but it's something that will appear helpful to us as we proceed here. That will be, I think, you'll see will be very helpful. So the first way to find incompatible base pairs is by studying the target cells. Now, let's take a look now at a couple more interesting cells that are waiting for our attention. And I'll highlight them first for you, and then we'll have a look at what's going on. So I'm going to highlight this cell. Oh, not this. I don't want the cell. I want the candidate. I want 3 and 5, 3 and 5, 3 and 5, 3 and 5. Okay. Now, let's have a look at what happens now. There's something very interesting going on with 3 and 5. What we can see is that, and what I'm going to be able to illustrate for you in a minute, is that the combination of base cells 3 with 5 is an incompatible base pair. We've already established that 3 and 9 are incompatible base pairs, but there's another incompatible base pair, and that is 3 and 5. Now, seeing this is a little more elaborate, but it's not too bad. Now, let's suppose, and the way this is argued, I'll illustrate here quickly. It has to do with the positioning of 3 and 5 in the cover lines. So let's suppose that 3 and 5, and I'll highlight them here just for illustration here. I think it won't hurt to have them highlighted there. I'll take the highlight off in a minute. But notice, there's something interesting here. If we were to establish that the cells row 1, columns 4 and 5, and row 6, columns 4 and 5, were essentially alone with only 3 and 5, we would have what is often called a deadly pattern. Right? The combination, if 3 and 5 end up being the only cells left in those 4 cells, that's called a deadly pattern, because we would then have the unacceptable situation of the puzzle having multiple solutions. Okay, but it's worse. We can see that the 3-5 combination in row 1 is also possible in row 8. David P. Bird refers to the UR threat here, or the deadly pattern threat, that comes from these 2 sets of possible unique rectangles, the URs. Now, what we're going to see is that if in fact the base cells contain 3 and 5, that one of these 2 UR threats must happen. And that we will then see is impossible. Okay, let's suppose that we have 3 and 5 here. That means that 3 is in target cell 1, and 5 is in target cell 2, or 5 is in target cell 1, and 3 is in target cell 2. It turns out that in both of those circumstances, let's look at the first one just to illustrate this then. Let's suppose that 3 is in target cell 1 and 5 is in target cell 2. That again is implied. I may not have mentioned that earlier in the video, but the target cells not only must contain the base cells, but they must contain different base cells. I neglected to mention that. However, if we know that 3 and 5 are the base cells, they are then the true or known base cells, then either 3 is here and 5 is here, or 5 is here and 3 is here. Okay, so let's take the first example. If 3 is here and 5 is here, okay, that means that 5 must be here. And it means that 3 must be here. If 5 must be here, it cannot be here in this mini line. And if 3 must be here, it cannot be in this mini line. Well, guess what, folks? That means that if 3 is here and 5 is here, then we have the deadly pattern of 3 and 5 and 3 and 5. Because we've excluded all the other 5s in block 8 to these two 5s, and we've excluded all the 3s in block 8 to these two. And we get essentially a naked pair. If the base cells were 3 and 5, the base cell candidates were 3 and 5, and 3 was here and 5 was here. And now you're going to guess what's going to happen next. If the base cell candidates are 3 and 5, and if 5 is here and 3 is here, then that means that 3 must be here and 5 must be here. 3 must be there and 5 must be there. What's that mean? That means that 5 can't be here and 3 can't be here. That means that we have the naked pair 3, 5. I guess you would refer to it as, you'd refer to it as a hidden pair, but because 3 and 5 are the can only appear in these two cells in this block, then we see that 3 and 5 must be in those two cells. And what does that give us? That gives us the deadly pattern again. The UR thread occurs in both ways. So if in fact the true base cell candidates are 3 and 5, we either have a deadly pattern with rows 1 and 8, or we have a deadly pattern with rows 1 and 6. That is an illustration of the technique of incompatible base pairs. Now, it does involve checking the presence and locations of the cover of the digits 3 and 5 in the cover lines. Again, it's fairly straightforward. It's a pattern. It's an implication from the junior exoset pattern. What does that mean, though? So now we have that 3 and 9 are an incompatible base pair, and 3 and 5 are an incompatible base pair. Okay, we have now 2 incompatible base pairs, and what's in common with that is 3. Aha! Let's check now. What if 3 were here? That would mean that this cell would have to be either a 5 or a 9, but they're both excluded. Aha. That means that we now have one more exclusion that we get. Whoops. We get one more exclusion. And that is that this 3 cannot be in that base cell. Why is that again? It is because we have eliminated the possibility of 3 with 5, and we've eliminated the possibility of 3 with 9. And if 3 were here, the only possibilities for the second base cell are 5 or 9, and both are incompatible. Well, that then gives us my introduction then to the junior exoset pattern. It is the one in which there are 2 base cells and 2 target cells. And the target cells are said to be unaligned. And that is the most common form of the junior exoset with 2 base cells and 2 targets. Turns out there are junior exosets with 4 base cells and 4 targets. There are junior exosets with 3 targets. And there are senior exosets. All that are in principle available to human solvers. Now, general exosets are usually not available to the human solver. We'll leave that aside for now. There are circumstances in which one can show the exocet condition even though the pattern is neither junior or senior, but that's another topic altogether. Well, with that, I will then end this video on an introduction to the junior exocet.